Okay, thank you very much for the invitation to speak here. I'm very glad to visit St. Andrews. It's already been a very nice experience. I'm going to speak today about quantum mechanics, and part of this, what I take to be revolution in our understanding of the general nature of reality that's been ushered in by quantum mechanics. If you read the popular literature, so something like Scientific American, one's going to get the picture that quantum mechanics is an extremely strange theory with very paradoxical consequences. And in fact, there's a further strand of this popular literature that would make you think that quantum mechanics requires us to throw away traditional conceptions of rationality so that we accept things that normal, ordinary, rational humans wouldn't accept. So we have to accept sort of really wild consequences from quantum mechanics. Now, I think that's quite overblown, and one of the jobs that philosophers of physics have taken upon themselves, so thinking of their work is so important, is they want to keep people from thinking they have to accept such crazy irrational consequences of quantum mechanics. Now, I think actually that self-proclaimed mission among many philosophers of physics has actually gone a little bit too far, though. And so what I'm going to put emphasis on this morning is that I think a lot of what's gone on in the philosophy of quantum mechanics in the past 50 years has been part of an agenda. And the agenda is not announced usually explicitly. The agenda is usually tacit. So I'm going to explain to you, well, let me just be more explicit about that. The agenda is an agenda of ontological naturalism. Now, I want to show you today how that agenda emerges in discussions among philosophers about quantum mechanics. And I'm going to show you that some of the apparent great paradoxes that philosophers have discussed actually possibly, well, I'm not just going to say possibly, I'm going to say actually do arise out of an injection of an assumption of ontological naturalism. What this means then is that some of these paradoxes actually go away if you remove that assumption of ontological naturalism. So that's going to lead me finally to a discussion of where that leaves us. What should we do in response to this? And I think I'm going to try to be very pluralistic in laying out what the various options are depending on where you're starting from in terms of your metaphysical background beliefs. Okay, so I'm going to, over here on the right will be some notes I go through. And of course, this type is quite small, so don't overstrain. I'll read out the important parts to you. Okay, so quantum mechanics was, from its origin, thought to undermine ontological naturalism or some kind of materialism. So let me just read here for you a quote from Heisenberg. Heisenberg himself said, "Quantum theory has led the physicists far away from the simple materialistic views that prevailed in the natural sciences of the 19th century." That's Heisenberg, of course, one of the pioneers of quantum mechanics. And this was incredibly typical of the early way of speaking about quantum mechanics. Now, there were two strands in early quantum mechanics in terms of this view that it undermined ontological naturalism. On the one hand, there was what you might call the positivist strand. The positivists actually thought that scientific theories themselves weren't supposed to be giving us metaphysics. That is, scientific theories weren't supposed to somehow describe some bedrock fundamental structure of nature. They were more like calculational tools. And so this was part of the overall logical positivist strategy for eliminating metaphysics. We don't want even to talk about physics as giving us some deep insight into reality. Instead, we don't want to say exactly shut up and calculate, but we use theories as tools and we stay silent beyond that. There was another strand in early quantum mechanics, and that Heisenberg himself, there's some historical experts in the audience who could tell you this better than I could. Heisenberg sat somewhat in the middle of these two strands. The other strand was sort of a mystical strand. There was a strand that was represented by people like Pauli in his later career, who thought that quantum mechanics actually is more friendly to some sort of idealistic picture of ontology rather than materialism. So it somehow gives room to enter back in a realm of ideas, or a realm of, you might want to say, almost spiritual things. So these sort of two strands that coexisted and mixed, and there was, very rarely you find a pure representative of either strand. But these were the dominant views of quantum mechanics in the early part of the 20th century. So that, in a sense, is old history, and a history that a lot of people know. a history that fewer people know is something that's been happening over the past 50 years. And if you go to most philosophy of physics conferences, where these are conferences among just the specialists, so the very small group of people who would say, I'm a philosopher of physics, and you go to these conferences, and what's been happening in the past 50 years is very rarely announced explicitly. On a rare occasion, someone will say, oh yes, this is what we're doing. So here's what they're doing. They're looking back at the quantum mechanics of its first 40 years or so, and saying, this was all very bad, and this was people giving in to an impulse to give up on the scientific project, people giving into the impulse to allow themselves to be irrational, and we're going to fix that now. So the job of philosophy of physics now that we've reached the 21st century, is to become much more rational about this and to clear up those confusions. Often the prophet of this movement, people will cite this person with great praise, was the Irish physicist John Bell. And people will say, as John Bell pointed out, quantum mechanics in its very root is inconsistent, it's incoherent, it's broken fundamentally. So here are just a few typical, these quotations that I'll give you now are very typical. These aren't sort of surprising quotations in this literature. These are the sort of standard ways to start a paper on the foundations of quantum mechanics. So here's a citation from a paper by David Wallace, a philosopher at Oxford University. The paper is a survey of what's now called the measurement problem, taken to be the fundamental interpretive problem of the foundations of quantum mechanics. And here's what Wallace says about quantum mechanics. He says, we have no satisfactory physical theory at all, only an ill-defined heuristic which makes unacceptable reference to primitives such as measurement, observer, and even consciousness. So that emphasis there is mine, it's underlying phrases. Similarly, Wallace elsewhere says, the measurement problem threatens to make quantum mechanics incoherent as a scientific theory. And then finally, Jeff Barrett, a philosopher at University of California at Irvine, says, the standard collapse formulation of quantum mechanics is logically inconsistent. This is the quantum measurement problem. Okay, so again, these philosophers think it's not just that quantum mechanics is weird, it's not just that it brought in some change in our worldview, it is that quantum mechanics as it existed before we came on the scene was broken, it was incoherent, it was unacceptable, unsatisfactory. So one of the main things I want to do this morning is I want to explain to you in what sense they think it's unsatisfactory. What standards are they imposing that they think quantum mechanics doesn't live up to? Some of these standards, I'll claim, are standards that come from a prior assumption of ontological naturalism. And we'll try to sort those out, what they are. Okay, so in summary of that is I think the past 50 years or so, past 40, 50 years, the program has been to purify quantum mechanics to make it a theory that will help serve this ideological program of reductionism, physicalistic reductionism. Okay, so like I said, I want to show you where these assumptions come into the project of understanding quantum mechanics, and then I want to conclude by giving you a metaphysical taxonomy. So I want to explain to you, just based on what I take to be some fundamental metaphysical commitments or approaches to the world, how then you might understand what's going on with quantum mechanics. Okay, so now before I proceed, I just want to give you a quick, what I wrote down there is apologia. So I made a huge career mistake once by giving a version of this talk to a typical audience, that is an audience of philosophers of physics, guys who I've just been characterizing as engaged in this project. And what I discovered, and what is most of you of course know is true, is that within pure academic audiences, especially among philosophers, something like 99.8% of them are ontological naturalists, and think that to maybe come to the table with a background metaphysical commitment that's not ontological naturalist, so maybe, for example, mind-body dualistic, so maybe the sort of Cartesian dualism, they think is not only wrong, but actually someone would have to be crazy or in some way benighted to still believe such things, and probably in some way morally bad to believe such things. So if you give a talk like this, we think maybe that's a live possibility, the audience closes their ears immediately. Now, I take it this audience is a bit more mixed, people coming from theology maybe, people coming from philosophy, not philosophy of physics, and so I'm going to treat, at least it's a live option, that ontological naturalism is not the case. So that's my apologia, is I'm going to take that as a serious possibility. And also, what I'm going to say is I don't think anything I'm going to say, and this is not my intention, I'm not trying to make an argument today against ontological naturalism. Now, in one sense, someone might come along and say, yes, you are, because you're trying to give a picture that makes it look like things will be nicer if you're not an ontological naturalist. And maybe that's the case. But I think that ontological naturalism is something that's not very sensitive to data and arguments. It's a very deeply ingressed, as Quine would put it, deeply ingressed metaphysical opinion. And so people usually would be more likely to give up on an interpretation of quantum mechanics than to give up on their naturalism. In fact, they'd be more likely to reject quantum mechanics completely than to give up on their naturalism if they thought quantum mechanics was in some way undermining. So I'm not going to try to argue against ontological naturalism. Okay, so here's where I'll go from here. So first of all, I'm just going to give you a quick crash course on the normal, what you might consider sort of the standard presentation of this apparent inconsistency in quantum mechanics, or as people call it these days, the measurement problem of quantum mechanics. So for some of you, this is very old hat. You've seen this probably hundreds of times before. If I add anything to understanding of it, hopefully I'll be able to crystallize in a very short and brief presentation what leads to an apparent inconsistency. If you haven't seen these things before, clearly it's going to be very abstract and probably hard to swallow at one go. And so I'll come back after that and explain in a more qualitative fashion what exactly leads to this inconsistency. So I'll derive the measurement problem after telling you quickly the postulates of quantum mechanics that are supposed to lead to this. Then I'll explain to you where the observer, or questions about mind and body, come into this whole discussion. That's under the label there, mind meets measurement problem. And I'll then take, in sections 4 and 5, I'll tell you a little bit about how some philosophers have responded to this. My main reason for doing that is I think that you can see these from a sort of outside perspective as very defensive responses. That is, people scrambling to try to make quantum mechanics fit into what their metaphysical program requires. And I'll also speak briefly in section 5 about the standard approach to quantum mechanics and why people have thought that's broken. And I have some replies there, which I think often these reasons people have said that the standard approach or the orthodox approach to quantum mechanics is broken, again, display their worldview, background, commitments. And then finally, that last section is where I'm going to open up, I think, a more pluralistic discussion of how you might approach these things depending on differences in metaphysical views. Okay. So I'm going to give you now 3 basic postulates of quantum mechanics. These were things that were plugged into the theory from the very start as a means of explaining the phenomena. So as we all know, back in the late 19th century, early 20th century, there were experiments that were performed that were incredibly puzzling. Classical physics, the physics of Newton and his successors, wasn't able to accommodate this data. And so people were really struggling, playing around with the basic postulates of physics, trying to figure out how they could accommodate this data. And after some years of struggle, some tools emerged, quite technical tools, that are able to be used to calculate the predictions that you want to get for this puzzling data. So I'm not going to talk directly about real experiments. I'll give you some toy examples here, but my main emphasis is going to be on sort of the abstract structural postulates that were used to explain this data. Okay, so first of all, let me remind you of a fact from the classical physics of waves in media. So we know about waves and the fact that they can superimpose on each other. Okay, so if you have 2 sources of waves, at some points these waves will reinforce each other, so you get a larger wave. At some points there'll be destructive interference, so there'll actually be reduced amplitude at that point. The quantum physicists of the early 20th century knew, of course, about waves and how they superimpose with each other. They also knew about particles. And one of the puzzling facts about quantum phenomena is that they appear to display features of both wave-like and particle-like phenomena. So how are you to deal with this problem? Well, here's a thought experiment. Is suppose you were to send particles through two slits like this. Well, what would happen? If they're evenly distributed, well, you get these two lumps on the screen in the back here. Now, you might think of this on a given, so imagine you send now one particle through at a time. So there's one particle, you don't know which door it's going to go through, the top or the bottom door. Well, what should you say then about the state of the system at the end of this experiment when it arrives on the optical screen? Well, there's a 50% chance it will be in the lump on the bottom, 50% chance it will be in the lump on the top. This is what we now call statistical mixture. So in other words, the state of the system itself, we believe the particle is definitely either there at the bottom or there at the top. But before you run the experiment, if you're just sending the particle through, the state you would ascribe to the system, you would say, I don't know. There's a 50% chance it will go through the top, a 50% chance it will go through the bottom. This is a mixture. Now, another sorry, just change windows. Okay, great, thank you. Okay. Now, of course, contrast this with the case of a wave going through these two slits, and what do you get on the screen in the back? Well, instead of these two big lumps, you actually get the characteristic interference pattern, so you get these distributed strips on the background screen. Okay, so that's classical physics. Classical physics of particles, classical physics of waves. What happens now if you do this with quantum mechanical objects? So take, for example, electrons, which, by the way, when you say electron, you immediately think that's a particle. Suspend your belief about that for just a minute and think we're back in the early 20th century. We don't know exactly. We don't even have the word electron. We just know there's negative charge around the nucleus, and we have ways of detaching that and sending it through these screens, things like this. Well, what happens in that case? So we can just run through a few thought experiments. So what happens if we just open one of the two doors and we send electric charge through? Well, we get just one lump on the background screen, as expected. Nothing too surprising, except the one slight surprise is you'd think if this was a wave, that actually would spread out quite broadly on the background screen, but instead, every time it hits the background screen, there's a flash and a localized point. So it looks like a particle. It looks like something now we call an electron. So suppose now we do this experiment many times, and we have some sort of coin flipper that decides whether to open the top door or bottom door, but we don't know in a given case which one it will be. Well, what happens? Just like classical physics, we get a lump on the background screen at the top, a lump on the background screen at the bottom. So again, it looks like particles going through, sometimes to the top, sometimes to the bottom. What happens now if we open both doors? We let the electrons go and we get the interference pattern like this. So that, of course, looks like waves. Now, this is the kind of thing you can read about all over the place. This is a well-known fact. Let me just step right to the mathematical. So how do we deal with this? Now, we could deal with this just sort of at a metaphysical level and say, this is a wave, this is a particle. Once a philosopher said, let's call this a wavicle, right? That's solve the problem. Just take half of each word. But here's how the physicists solved the problem, is they just said, let's take a mathematical device as follows. So up here at the top, what I call superposition, they say, let's assume that the space of states, so a state of a physical system is just a complete description of the facts at a given time. So that let's assume that the states of a physical system, a quantum system, have this relation, or I should say a function on them, which we'll call superposition. Okay, so far it's undefined mathematical calculus, that is, we just have this plus operation, and we have two states, and we have a way of putting plus in between them to form another state. Okay. So far, no interpretation, no explanation of the empirical import of this assumption. Okay, that looks an awful lot. The fact that we can do this looks an awful lot like superposing classical waves, because with classical waves, we have a sum operation too. But in just a minute, I'll explain ways in which it's different from the superposition of classical waves. Okay. Second assumption, so we know what the states are now, just this abstract space of states that can be linearly added together. The quantities of the system are, now there's a fancy way to state this, and then I'll state the fancy way and then explain it in a little bit more of an intuitive way. The fancy way of stating is the quantities of the system are linear operators on that space of states. Okay, and you think, well, that takes a semester to learn exactly what that is, and yes, in a sense that's true, but there's an easier way to put this. Here's the easier way to put this, is this linear space of states, let's think of it, just for the moment. Just think of this in a two-dimensional way. So here's my two-dimensional plane here, and here's an origin. Here's what a state is like. It's a vector in this two-dimensional space. So that's a state. So far, nothing, just an abstract representation of the collection of all states. We have this way of taking two states, say this and this, and we add them together and we get another state, say here. So that was the assumption that we can superpose states. Now the quantities, I said they're linear operators, but here's an easier way of thinking about that, is anytime you choose a pair of orthogonal states, so this is not quite a 90-degree angle here, but if it were two orthogonal states, if you attach a number to each of the vectors, that gives you a quantity. The numbers you attach to the vectors are the possible values of the quantity. So now immediately you see something that you often hear about quantum mechanics. Quantum mechanics somehow discretizes things. That's a partial truth, that quantum mechanics discretizes things. The case I'm looking at here is a case of discrete valued quantity. So quantity has only two possible values. This value or this value. Okay? Now, going back to the fancy description, it turns out what I just told you is equivalent to the claim that the quantities are represented by linear operators by some known results of linear algebra. Linear algebra shows you that certain linear operators correspond to bases, that is, these orthogonal unit-length vectors, and then numbers attached to them. Okay, so I told you what the states are, what the quantities are. Now let's start to put some empirical content onto this formalism. Okay, when the system is in a certain state, say this, and I measure a quantity, say I want to say I know the system is in this state, and now I'm going to check the value. I would say let's make a prediction for, say, the quantity that's represented by this pair. And let's just, for simplicity, let's put a +1 associated with this and a -1 associated with this, and call this quantity A. So A is the quantity that assigns +1 to this, -1 to this. And I say, if the system is in this state, what's the chance that if I were to make a measurement, this quantity A would have the value +1? Now something I'll tell you, the first fact empirically is A will never have any value besides +1 and -1 when you measure it. So of course one's tempted geometrically looking at this picture to say, well, A is going to have the value something like 0.75. But you never see that. So you go out and make a measurement, A is always +1 or -1. It turns out the chance that A is +1 depends on how close this state vector is to this axis. The chance that A is -1 depends on how close this state vector is to this axis. That's called Born's rule. So Born's rule just says that's how you should compute probability. So Born's rule is a sort of a methodological stipulation. If you want to know the chance of getting a certain outcome, calculate as follows. And it turns out it's incredibly successful. This is the one, if anything else about quantum mechanics, we're wrong about everything else. This we're right about. That's how you calculate measurement, the probabilities of measurement outcomes. Okay, so that's essentially the entire, in one sense, the entire statistical algorithm of quantum mechanics. The core idea is based all around that. Okay, and it's, of course, incredibly abstract, but also incredibly simple. Now, tying this back to the example I was giving you of the two slits, what happens there? Well, we think now that when you open the two doors on the screen, the state of the stuff going through there is a superposition of bottom and top. So you might call, say, left, right. So the way this might sometimes be written would be like this. Okay, and normally we have, I'm just going to assume when I write like this without coefficients, just trying to simplify, I'm going to assume these are equally weighted. So in general what you can do, so this is the sum, say this is left, this is right, this is an equally weighted sum of the two. I'm never going to need to deal today with cases where you're off that equally weighted scenario. So we think that when you open both these doors, the state of the thing is a superposition of left, right. And that gives the correct predictions that if you set up, for example, a detector on top of the two doors and you say, let's see which door the stuff goes through. Does it go through the left door or the right door? In 50% of the cases, it will go through the left door. 50% of the cases, it will go through the right door. So the probability, if you measure which door it goes through, is 50-50. Okay, so that makes a correct prediction about what you would see. Now, I need to add a qualification here, which is a little bit of a sort of advanced thing, but it's something that people make mistakes about a lot. So I want to go ahead and try to prevent these mistakes right now. One is tempted to think at this point to say, well, when the system is a superposition of left-right, it's in this amorphous world of not having any property. It's not in the state of going through the left door, and it's not in the state of going through the right door. So it's somehow not become objective reality yet in some way. This might incline you to think there's some sort of idealism built into the very roots of the theory. But every quantum state is a superposition. Okay? This state is a superposition, as I've written explicitly, but so is the state left. It's a superposition of some other states. That's obvious if you remember that superposition is just this linear combination of vectors like this. Take any vector in this two-dimensional plane. I can find you two other vectors of which it is the sum, two distinct vectors. So the state left, going through the left door, is a superposition of some other states. Now, what that means in particular, and also remember what I said, that quantities correspond one-to-one to choices of orthogonal vectors in this space. So in particular, every single vector is a state that's definite for some particular quantity. So left plus right is a state in which some quantity has a definite value. In this case, it's probably a state of motion because in quantum mechanics, position, the quantity position where I'm located in space, is complementary to the quantity momentum. So this is a superposition of position states, which is probably a definite state of the momentum quantity. So when you're in the state left plus right, it means something like moving as opposed to stationary or something like that. So I'll return to this in a minute. But it's just important to remember that it's not as if in quantum mechanics we have some states where ontology is clear, where we know what's going on, and other states where things have gotten murky because we're in superpositions. No. Every state is a superposition of some other states. So we're going to have to deal with that problem at some stage, no matter what. Okay. Now, the first interpretive supplement. So I said Born's rule, you have to buy that no matter what. If you're going to use the formalism of quantum mechanics, you have to use Born's rule. Now, a common interpretive supplement to this, which is very natural, in fact, I've already been speaking in ways that sort of presuppose this, is what's called the eigenvector-eigenvalue link. Now, the names come from linear algebra, but basically, and so I'll just use EE link from now on. This is the claim that a quantity has a value at all. So this is something that already sounds metaphysically strange. What would it mean for a quantity not to have a value? But for a quantity to have a value at all, the state of the system has to be one of the vectors. So I said every quantity corresponds to a pair of orthogonal vectors. The state of the system has to be one of those two orthogonal vectors for that quantity to have any value at all. That's an assumption that was implicit, for sure, in the early days of quantum mechanics. And in fact, I would say it was probably, again, historians can tell us later whether this is correct, I would say it was probably not until, say, the 1960s with work by people like David Bohm, where it became very clear that you didn't have to accept this principle. Okay. So, in application to the scenario I've been describing, if you accept the eigenstate eigenvalue link, which is a part of the orthodox understanding, the traditional understanding of quantum mechanics, when the system is in this state, left plus right, superposition of going through the left door and the right door, it doesn't have a position in space at all. The quantity position is not defined in that state. If this is, however, the state, say, moving as opposed to stationary, then this is a state in which the momentum quantity has a value, if you accept the eigenstate eigenvalue link. In contrast, if the system were in this state left, going through the left door, that would be a superposition of, say, moving and stationary, and so by the eigenstate eigenvalue link, the system would have no value for momentum. There would be no answer to the question, is this thing moving or stationary? Okay, so now we need to add, we're going to gradually work ourselves into this apparent, this supposed paradox, this supposed crisis or inconsistency in quantum mechanics. We haven't seen it at all yet. We can see the first instance of it as soon as we talk about the rule for change of state over time in quantum mechanics. So we've been talking about the kinematics, how things are at a time. Let's talk now about the dynamics. So how do things change over time? The simple fact is that the laws of quantum mechanics, the rule for changing state over time, is linear. All that means, written up here in very small type under linear dynamics, is that if you knew, let's just look at these guys here, if you knew, say, this state plus 1 over time, let's say 1 minute, if you knew it would go here, and if you knew over 1 minute this state would go here, then it follows, according to linear dynamics, that any superposition of those two would go to the superposition of those two. That's a simple fact. So in other words, you can calculate where any state would go over time once you know where states in an orthogonal basis, these states that are orthogonal to each other, once you know where those will go, you know where any sum of those two will go. Okay. That seems, at this stage you might think, why in the world would I believe that? Well, again, the simple fact at this stage is if you believe that, you make accurate predictions. So in other words, when you're describing a system, you do all these calculations, you figure out what its dynamics are, assuming those are linear, you let the system run, you make a measurement, and you find out it was incredibly accurate. And so by normal sort of hypothetico-deductive reasoning, you assume the assumption of linear, you conclude the assumption of linear dynamics is a good one. It makes good predictions. Okay, now we start already though to get the first flavor of the measurement problem, the crisis, because here's what happens. Is suppose the system, so I can say this in a complete abstract way, suppose our system is in the state left plus right, the superposition of going through the left door and the right door. Now, let's go take a look. Let's put a detector on top of, say, the left door and take a look. Is it going through the left door or not? Now, our measurement will have an outcome. It will either say yes or no. The detector will either click or won't click. And by the eigenstate eigenvalue link, what that means is when I make the measurement, the system has gone from this state, left plus right, into the state just left. So it's as if things evolve under the standard dynamics when nobody's looking, but as soon as somebody looks, and this is why it's called sometimes a collapse of the wave function, it collapses onto one of the terms. It collapses if you're measuring a certain pair of orthogonal vectors. if the state were here originally, it collapses to the outcome value that you obtain. Okay, now what I've said so far doesn't obviously contradict linear dynamics, but the suspicion that there'll be a contradiction should be arising, and it's going to become more apparent soon. Okay. So to this stage, actually, one could pretty much, using the tools I've described, filled out in much greater detail, one could make all the predictions you need to for measurements we know how to make. But the way that the problems for quantum mechanics are often described, we have to actually add some information about how you represent composite systems. The reason is, when people started to ask about whether the formalism of quantum mechanics is adequate, whether it makes sense conceptually, one of the first things they said was, let's put the observer, the guy making the measurement, let's put him into the picture too. And so we have to describe him as a quantum mechanical system, and then we'll see how things work out there. Okay, so that's what we need to describe composite systems. Okay, so the basic assumption that goes into representing composite systems in quantum mechanics is that the quantities of two distinct systems are logically independent. Now all that means essentially is that we can mix and match the values, and by we I don't mean necessarily in practice you could go out and manipulate these. I mean these are possible states of affairs. So suppose that you have two of these two-slit experiments, and you think that these are independent from each other. So, for example, they may occur in distant parts of space. If they're independent, what it means is if I measure which door the things are going through, and I do this many, many times, in some cases I'll see them both going through the left door. Sometimes I'll see this one going through the left, this one through the right, and vice versa. So all that mix and match of all the different possibilities. That's characteristic of what we think of as logical independence of quantities. Now, here's just a purely notational convenience. It's very hard to read it here. Actually, it's under the black thing right now. So I wrote up here states in Greek letters. So psi and phi. And by eigenstate here, I just mean an eigenstate is one of the states. An eigenstate for a quantity is one of the vectors, where I said a quantity corresponds to an orthogonal pair of vectors. An eigenstate is one of those. An eigenstate for that quantity is one of those pairs of vectors. If you have two quantities that are logically independent from each other, here's a way we can represent the combination where they have, so suppose one can have value +1 and the other can have value -1 simultaneously. Suppose this is state psi and this is state phi. Well, here's just a notational convenience. As I put this fancy looking tensor product operation between the two, which is on the third line of that definition. That little circle with the cross in the middle is just saying that's logical combination of the two states, assuming that's possible. Okay. So now here's an assumption, the assumption that is probably the most opaque in building up the foundations of quantum mechanics. And yet, once again, it makes correct predictions, so we believe it's a good way to write down the formalism. The assumption is that superposition of two vectors distributes over composition in this way. Now actually this has a, no, it does not have a typo there. Next line has a typo, but this line, assumption, composition distributes at the very top there. So in other words, if you have superposition on the left, psi1 plus psi2, and you compose with phi, that's the same state as psi1 composed with phi, superposed with psi2 composed with phi. Now, I won't talk through this at the moment in order to save time, but if you think about it for a minute, you can see that's a pretty, empirically speaking, if you were to make measurements, that makes a lot of sense to do that, to distribute superpositions over composition like that. Okay, one consequence this has, though, is that, and this again also, there's no reason to disbelieve this, is if you take two quantum mechanical systems, each of which has superpositions, you put those together in a composite system, that system also has superpositions. Okay, that makes perfect sense. But this has an incredibly profound consequence, a very troubling, in a way, consequence, and that is there are these things called entangled states. and that's the typo right there, is that actually between psi1 and phi2 should be a tensor, not a plus. So that's a composition of those two states. So here we have a state that's a superposition of, on the one hand, the composition of psi1 and phi1, and on the other hand, the composition of psi2 and phi2. So this is a state where the two systems are strictly correlated. So in other words, if we go out and make a measurement and we find that this first system is in psi1, then definitely the second system will be in phi1. And if we go out and make a measurement and the first system's in psi2, then definitely the second system will be in phi2. So strictly correlated, which by itself, that's not puzzling. And we have lots of cases in classical mechanics where things are strictly correlated. What's puzzling now is if you go back to the interpretive principles we've already brought on board when we were talking about superposition, is this is a state in which the individual systems have no definite properties whatsoever. That is, this state is not an eigenstate for any observable pertaining to the first system, and it's not an eigenstate for any observable pertaining to the second system. So, to put it bluntly, or to put it even maybe hyperbolically, is both systems have lost all reality as individuals. They're strictly entangled with each other. Okay. Now, this stage already, this boggles classical metaphysics, I think. So already, even the very first stage, superpositions, is something I never would have understood or thought I understood until I learned the formal recipe of quantum mechanics. So superposition says quantities that you think describe things in the world, in fact, actually don't always describe things in the world. That is, there are states in which things you thought all physical objects had, they actually don't have them. So there are physical objects that in certain states don't have positions. That I find very strange. The second feature, so dynamics, well, that's a more technical thing. We'll see how it leads to problems in the middle. But this composition principle and entangled states is even harder to understand. Because now you have things where you think of a physical object, and it's not just that it has this complementarity where some quantities lose their status, others gain their status, but now you have states where these objects have no features at all. They're featureless. So this already, we could stop right now in a sense, and we don't need a measurement problem per se. We have what somebody called a reality problem. 15-minute time. Thanks. Okay. So, but now we can be explicit with the assumptions we've laid down and derive this supposed crisis or inconsistency or incoherence. Okay, so here's how it goes. It's very simply, I'll go through this quickly because it's not conceptually deep. It's just putting the pieces together that we just laid out. Is if we have a reliable measuring device, well, here's our measuring device. Here's the system we're measuring. We're going to talk about the composition of those two. If this is reliable, the measuring device at measuring a certain quantity, say the quantity that corresponds to psi1 and psi2, well, if this system's in psi1, I should go to the systems in psi1 on the measuring device. If this system's in psi2, I should go to the measuring device should say the system's in psi2. So that's just represented here. That's saying if you have psi1 and then phi0 is the ready state of the measuring device, saying I'm just ready to make a measurement, well, you go to psi1 and phi1. Same with psi2 and ready, we go to psi2 and phi2. Given that basic assumption about what a reliable measuring device would do, quick argument, you get that at the end of the measurement, the measuring device has no properties, which of course is not what we had hoped for, right? Because we wanted the measuring device to end up telling us what state the system was in. But if we start the system in this state here, superposition of psi1 and psi2, then just by distributing that superposition over the ready state like this, because that's how composition relates to superposition, then using the dynamics, the fact that they're linear, we end up with the joint system in this entangled state, psi1, phi1, psi2, phi2. So entangled, therefore the measuring device has no definite properties whatsoever. Okay, Now, in a sense, what I've just said is not surprising any more than entanglement itself is surprising, except that we care about measurement and we want to do measurements. But if we already accepted there's entangled states, the fact that a measuring device can be entangled with the object it's measuring, well, we already knew there were entangled states. Where it really becomes problematic is where we put ourselves back in the picture. So suppose now we think of the measuring device is me. I want to go out and I want to see, is the system in state psi 1 or psi 2? So let's redescribe this measuring device now. Let's say chi 0 is the state in which I am alert and attending to the measuring device. I'm looking to see what it says. Psi 1 is the state in which I believe it says. Here I have A subscript I, so A1, you can think that's the state, psi 1. Well, what happens to me? Just run the same argument over again, and at the end of this measurement, the system being measured, the measuring device that I'm using as a tool, and my mental state are jointly in the superposition. And so what does that mean about me? It means I have no definite property at all. I don't believe it's in psi 1, I don't believe it's in psi 2. So this is a horrible crisis, right? Quantum mechanics is literally inconsistent. If you take it seriously, take the postulates seriously, then you can't do measurements, you can't figure out that it's true. Okay, now, one could spend a long time at this stage talking about how various people respond to the measurement problem. I'm just going to pick out a couple of these so I can move on to my last points. So first of all, notice, and I'm just going to say this is a preview for what's going to come later, is we could stop things right now or at least get hung up. So this is this line up here. So this here is we could stop things now by saying, wait, something seems very fishy at this point because you wrote down, you tell me, you say you wrote down chi sub 1 is the state in which you believe that the system is in psi 1. And I then start doing physics. But my state of believing that something is in a certain state is not a physical state, is it? So it seems kind of funny to apply the apparatus of quantum mechanics not just to some physical object we can test in the laboratory, but to my beliefs and things like that. Now, of course, if you're a reductive physicalist and you think beliefs are just physical things, then of course you would do this. But if you're not, you might be a little bit worried at this stage. Okay, so skipping over this, I'm just going to tell you very quickly what some people say to deal with this problem. So I said these philosophers of the past 40 years, this is the typical way people do this. Set up this big crisis. Students are supposed to go home and panic, right? I don't know what the world is like, and then you're going to fix their panic by telling them your preferred solution. What are the preferred solutions? Well, there's the good old hidden variables, Bohmian mechanics. So in other words, we just say that when we thought that the system was just in a superposition of going to the top door and bottom door, in fact, there was a secret hidden variable that said which door it was going through. That's essentially the strategy of Bohmian mechanics. Very attractive solution in the sense that it's not hard to be a scientific realist if you accept Bohmian mechanics. I'm not even going to say what my objections are. I don't like it as much as the next guy does. I want to move on to something that's a little bit more dominant these days in thinking about these things, and also more dominant in sort of the idea that quantum mechanics was broken, it doesn't fit into my naturalistic worldview, now I'm going to fix it so it does, and this is the Everett many worlds approach, which instead of denying any of the postulates of quantum mechanics, Everett many worlds says, we were wrong to think that at the end of the measurement, we believe that the state is either psi 1 or psi 2. In fact, what happens is we really do become entangled. And you thought you were just one person who believes that the state was psi 1, the state is psi 1 or psi 2, and you were wrong. So you were totally wrong about what the world is like and about what your relation to the world is like. Okay, and again, I'll skip my objections to that. And in fact, I'm going to skip orthodoxy and replies, which I could bring up in the question and answer period, and go on to what the taxon that I wanted to finish with. Okay, so what we have now is there's a sort of standard way of doing quantum mechanics, what you might call orthodox quantum mechanics. that actually basically stops, when I said dynamics, I had these sections. I had the section on superposition, the section on dynamics, and the section on composition. The orthodox approach to quantum mechanics essentially stops after the dynamic stage and doesn't go on to analyze the person, the observer making the measurement in terms of composite systems. And so in fact, if you learn quantum mechanics as a practitioner, you never need to know how to apply quantum mechanics to yourself, because your job isn't describing your own interactions with the system. Your job is to go out and make predictions. And it works. We all know it works very well. It makes very good predictions. It's earned people a lot of money. And one could just stop right there. So why not? Why stop? Why not stop right there? Why not just say, when we go out and make a measurement, the state collapses, we don't know why. We know we have probabilities for which state it will collapse to, and these are pretty accurate. So why push further than that? Well, down again. Well, here's one very good reason to not stop at that point. If you're an ontological naturalist, and you feel that it's incumbent upon you to explain knowledge, belief, all the phenomena of human experience in terms of basic physics, then one might see that orthodox quantum mechanics is not satisfactory for that purpose. Because orthodox quantum mechanics does make reference to things like making a measurement as a primitive instead of analyzing that. Or if you go on to add a little bit of an interpretive supplement and say, well, what really happens, what makes the state collapse is that there's a conscious observer. Well, surely, if you're an ontological naturalist and your job is to explain all that stuff in terms of the physics, you can't use that stuff as basic primitives in your physical theory. So that would be a very good reason not to stop there. To not stop there and keep going. So suppose that you're not an ontological naturalist. And I said I assume there are a few people in the audience who don't think this is an obvious point of view. It's something that's intellectually mandatory. Now, there's basically two strategies one could take up at this point. The first strategy, which I think is sort of the more obvious strategy, and that is if you're, say, a mind-body dualist, well, you can do dualist science. So following a suggestion, I'm going to appeal to a sort of larger suggestion voiced by, among others, a philosopher named Alan Plantinga, who said, if you're a theist, for example, then you shouldn't be abashed to do theistic science. That is, if you believe God exists, and you believe you have knowledge about God, then that knowledge, the facts that you have, should be permissible in constructing scientific theories, and so on. In the same way, if you were a mind-body dualist, and you think you have independent reasons outside of current physics for being a mind-body dualist, shouldn't you then try to build a scientific theory that takes all the facts you believe you know into account, that saves all the phenomena? So you could do what you might call dualistic science. That is a science that describes physical stuff, mental stuff, how they interact with each other, and you could work out theories in that vein. Now, there have been philosophers and physicists who've done this. So Henry Stapp, for example, a physicist at Berkeley, he has explicitly assumed mind-body dualism, working out an idea that Eugene Wigner originally had, trying to give an account of quantum mechanics that takes dualism seriously. So that's certainly a possibility. Another possibility, though, is it could be that you're a mind-body dualist for some reason independent of quantum mechanics, and yet you think somehow in doing physics that shouldn't necessarily come into play. And this could be for various reasons. One reason could be purely pragmatic, and that is suppose that, so let me speak first of all on slightly, so pragmatics can be a bad thing or a good thing, right? Pragmatics in some cases is bad because you're just trying to maybe cutting corners to try to get ahead in life. Something like that. Well, here's the way you can cut corners, right? Suppose that you're a mind-body dualist, but you want to get your physics degree, and you want to get honors or whatever, right? So you're not going to mention it to your professor. You're just going to do physics as if it weren't true. Okay, so that's a sort of bad side to it, but there's a good side to that too. And the good side is that most of us sitting here believe there's some human good in doing science, and it's a common good that people with different background beliefs share. So it's good to do science collaboratively with people who don't share your metaphysical background beliefs. That might be a good reason, even if you're a mind-body dualist, not to try to do dualistic quantum mechanics. You might think, hey, we need to do research together. That guy's an ontological naturalist, I'm a dualist. We've got to meet in the middle somewhere, and so let's bracket our metaphysical beliefs. So that would be sort of pragmatic justification for saying, even if you're inclined to believe mind-body dualism, don't bring in quantum mechanics. But I just want to float one more, slightly more, not pragmatic, but principled reason, and this is very much a question for open discussion because I don't know the answer at this stage. And that is there something in the very nature of physics as an intellectual activity, not just pragmatically speaking, but is there something about physics that makes the mental intractable to physical investigation? So there's something about the demands of modeling physics that would make us exclude description of, say, mental states from the physical. Now, I don't know the answer to that question, but I think it's an intriguing possibility, one that certainly is supported by traditional dualistic views like Descartes, who thought that physical stuff was different in nature from mental stuff. So the question I want to leave you with then is, if someone is not an ontological naturalist necessarily, do they have reason to think quantum mechanics is broken and needs a fix? That is it enough not to be committed to the ontological naturalist agenda, to be happy with quantum mechanics in its orthodox formulation? Or is it required for all of us in intellectual honesty to do something to change this, to improve the foundations of this theory? Thank you.
Ladies and gentlemen, I think you'll agree that was an absolute tour de force. And actually, can I strongly recommend to you a paper by Hans called The Measure of All Things, Quantum Mechanics and the Soul, which covers the same territory. And I find it an extremely illuminating paper and goes very well with the talk. Just a quick elucidation. So we have a problem that basically entanglement and superposition scale up from the microphysical level right through to the macroscopic measurer, her brain, and so on and so forth. And that's really the source of the measurement paradox and measurement problem. And what you're saying is, actually, we can immunize or quarantine the observer because we now invoke another kind of substance, which isn't, as it were, we can disentangle, if you like, the observer. And I think I'm very sympathetic to that, because one of the things that worries me a lot about discussion in contemporary physics is the confusion between a measuring device on the one hand and an observer on another. And of course, the measuring device will indeed be entirely entangled, will have a superposition and so on. And what you're saying is the observer, even the observer's brain, the measuring device and the observer's brain are not to be confused with the observer. That's really your central point, isn't it, I guess? I just want to be sure I got that right.
Yes. I think that encapsulates it. I mean, I'm only a little hesitant because it seems, the way you state it, which I think is accurate, it seems so negative, right? So it seems like we're just saying, leave this alone. It's almost like a sort of Kantian, let's leave room for faith, right? Which seems awfully negative. And yet my impulse is in that direction. My impulse is to say there are things that we don't know how to bring down, things that we don't know how to reduce to the physical. And actually the impulse to do so is mistaken. And that's what I feel about the observer. I think the impulse to reduce the observer to the physical is mistaken.
And I warm very much to that. Now, we had the original Simpson Palace shift, where we moved the starting time. So we're going to have a proper, just under a quarter of an hour Q&A. And the subsequent speakers mustn't feel their time is going to be used up. We've just had a shift. So, ladies and gentlemen, your questions perhaps. Yes, Andrew, I think you're also going first, and I apologise if I miss people.
Thank you very much indeed. It's a wonderful talk. It's very good to hear a philosopher competently explaining quantum mechanics to physicists, because often we don't get that. And it helps to see things we're familiar with from a new angle. Very grateful for that. It's interesting when you look at the other possibilities for how to deal with the world. I've got no problem with bringing in God. Of course, God is obviously too powerful. It's like get out of jail free card. So it's always a little bit wary to bring that kind of first cause in immediately. But I wonder whether we need to extend naturalism, because naturalism before the Cartesian revolution included all kinds of other things, like forms. And even the term soul was just the form of a living thing. I suppose you could also say persons, for example, as all parts of the ontology of the world. So can we actually extend the ontology? Is it really that we need to extend naturalism a little bit more to include some of the things we've become less familiar with talking about in philosophy?
So in terms of a programmatic vision, I feel I have very few recommendations to make. But so in terms of the negative side of what counts as natural, I agree that boundary has been very ill-defined. And yet it often is used as a sort of, socially speaking, it seems like it's used as sort of cudgel, right? To say, like, I don't like it when you talk about this, that's not natural. So, and the current demarcation, actually, it's a very sort of funny historical thing, is it seems to take natural to correspond to the Cartesian spatial, so to speak, which is such a restriction from, say, the Aristotelian view, which include many non-spatial sorts of things. I personally think would prefer to just not use, not myself understanding the demarcation natural, non-natural very much. I prefer to sort of get rid of that term as much as possible. I think possibly a more descriptive approach would be something like, what types of things do we try to fit into the scientific nexus, so to speak? That's probably just another way of saying natural. And I think it's an open question to what extent things of one might almost say, spiritual nature, so human minds and so on, to what extent we should attempt to bring those into the scientific nexus. My own inclination is current physics is a mistake to try to do so, and that's possibly due to limitations of current physics. So I find it quite humorous when people say, here's quantum mechanics, let's now talk about mental states in quantum mechanics, because quantum mechanics is nowhere close to having the sophistication to apply to such things. We don't even know how to apply quantum mechanics to portions of the human brain. So, just to say is I think that as a long-term future vision, to say we shouldn't truncate, we shouldn't necessarily put an a priori prohibition on how far the scientific nexus can go. And yet, at the current stage of knowledge, I think we should be hesitant to push things in too quickly.
That's a rich topic I hope we're going to pick up again in the general discussion. I saw lots of hands, and gentleman there, if I may, and then gentleman there. I'm sorry if I'm unjust.
Regarding your methodological question, I like the idea of encouraging dualistic science. In fact, if there was dualistic science, more dualistic science, it would be more bitter dualistic science. A lot of it is not very good so far.
Yeah.
Stat does very intriguing things and so on. The question is whether the medical problem is giving us the right clue for where dualistic science might be useful. And just to cut a long story short, I'll do the usual thing and coach John Bale. When he says, did we have to wait until the evolution of organic life before the first collapse of the wave function, or did we have to wait a little longer until observable PhD? The question is, you did mention the reality problem. The fact is...
It's a very long question. I feel sorry for Hans. He's stuck in that distance of the shocker. But can I just check, can everybody hear the question? No. So perhaps give us one quick question amongst that you would like Hans to respond to.
Maybe I've said enough for Hans to get the gist of the question.
So on the one hand, Bell's issue doesn't bother me because I think we really have to take, so to speak in the lingo that we share, so we really have to take the eigenstate eigenvalue like seriously, right? So all this talk about before there were conscious observers, before there were PhDs, And what, by the way, what institution do they get their PhD from? If you take the eigenstate eigenvalue link, there still was reality at that stage, right? It's not like there was no reality to all human beings. So it's not an idealistic interpretation. It's not saying there's nothing outside of observers' minds. Now, that doesn't really, so someone who's really acquainted with the measurement problem and its full ramifications, that doesn't really get to the issue of it, because the question isn't, was there reality prior to observers? It was, did it develop in the same way? And if you believe that human observers cause collapses, then we actually are being on the scene, and PhDs being on the scene or whatever, changes the history of the universe in a way that you wouldn't sort of expect. And we do think that, like, locally, you can move things around, but collapsing wave functions, that's an awful lot of power for humans to decide which things are definite and not. So do I think that sounds funny? Yeah, I do think it sounds funny. I don't think it sounds funny enough, just to put it the extreme hyperbolic opposite case. I don't think it's funny enough to go on and then develop a full-blown Everettian inflationary metaphysics. That seems more puzzling to me, but that's probably personal preference.
Thank you. Next question.
It's not clear to me how mind-body dualism solves the measurement problem, because substance dualists typically think that correlated to a mental state, there is a physical brain state, even if the mental state isn't caused by the physical brain state. And the brain state would certainly be describable by quantum physics. So if that's in an indeterminate superposition, so would be the correlated mental state.
So I did research on this in one of my earlier phases where I was explicitly undertaking dualistic science approach to this. Is I asked the question, would it really solve the measurement problem? And I think so again, because I don't know that I really believe this. I don't know if I have enough evidence to believe this, but there is a way to solve it. Here's how one can solve it: is treat mental states as definitely distinct from physical states. That's step one. So they're not identical, they're distinct. Now let's actually do some real physics with this. The first step is to now look just at the mental states themselves and ask what structure do those have? And do they have superpositions? And I think the answer is there's no reason to believe they do. So they don't have superpositions. So let's stick those two together. Physical states that have superpositions, mental states that don't. And let's run dynamics. And actually I've got a model where everything pops out nice and clear. So you solve the measurement problem, it all works. The only reason not to believe it is, what evidence do we have that mental states are really like that? So it's a bit speculative. But so I think, if one uses sophistication, one can implement a dualistic solution.
Is that paper published somewhere?
So fragments of the idea are in the Soul Hypothesis paper. And I have more details written down in my desk drawer that I can send to interested parties.
And last, I have to draw this bit of the discussion to a close and hand over to the next chairman. I think, Simon, you're chairing the next session. Meanwhile, Hans, thank you for a fantastic start.